A special case of the LU decomposition is the so-called Cholesky decomposition. There are two conditions in order to be able to apply the Cholesky decomposition. First, our coefficient matrix should be a symmetric matrix, and second, it should be a positive definite matrix. And in MATLAB, it is easy to check whether a matrix is symmetric or not, and it is also easy to check whether a matrix is positive definite or not. In order to check the symmetry, what you need is basically the transpose of the matrix should be same as the original matrix. And in order to check the positive definiteness of a matrix, which is our coefficient matrix A, you need to make sure all these eigenvalues are positive, actually. So if these two conditions are satisfied, then we can directly use the special case of LU decomposition, which is the so-called Cholesky decomposition. And in this decomposition, different from the LU method, we can directly decompose our coefficient matrix A in terms of only the upper triangular matrix. So this is upper triangular matrix transpose times the upper triangular matrix U. Here's an example. If you are given a matrix in MATLAB, like this one here, and you can easily verify that this matrix is symmetric, and second, you can verify whether the eigenvalues are all positive or not. And if we apply the eigenvalue function in MATLAB, we obtain lambda 1, lambda 2, and lambda 3. And as can be seen, all of these values are positive, and therefore we have a symmetric positive definite matrix where we can apply the Cholesky decomposition method. In MATLAB, this can be done by using the Cholesky function here, and it's going to directly produce us the upper triangular matrix U, which is what we need in order to decompose our coefficient matrix A. So this is actually, instead of A, you can directly write U transpose U, and this will solve our system of equations. And for this example, the solution is given as -1, 0, and 1. Another interesting example you can consider where we have a system of linear equations to solve is the least squares estimator. In the least squares estimator, which you might know from your earlier statistics courses, the coefficients that minimize the residual sum of squares is given actually in terms of this beta equation here. How we obtain this is actually simply coming from this minimization problem. So this is the residual sum of squares from our typical regression problem. So where you have the data x and you have some coefficient vector beta, and you have these residuals e values. So let me write this a bit more clearly. So these residual sum of squares can be minimized with respect to our choice of the parameters, beta. And this is a minimization problem, as you can see here. And basically this is what you get from this multiplication is a scalar. So if you multiply these term by term, you get this next equation here. And notice that these two terms over here, these are scalars. And since these are scalars, transposing these doesn't matter, and we can collect them under the -2 beta transpose x transpose y value here. So notice that if you have, let's say, n observations in this regression, and if you have d parameters, basically the size of your beta vector is d by 1, and you can verify that what you have here is actually 1 by d, and then your x, which is your data, this is going to be transposed, so this is d by n, and then your y, this is your dependent variable, it's a vector of n by 1. So what you can see is it is actually a scalar, and transpose of a scalar is also the same thing, so we can combine these two terms together, and we have the last term here. And if you take the first order derivative of this expression with respect to beta, and if you set it equal to 0, you can obtain the least squares estimator beta. However, you can notice that this is simply a system of linear equations, and actually obtaining the beta solution by matrix inversion is not a preferable method. And rather than using the matrix inversion directly, again, LU decomposition can be applied in this example as well.